In 2016, astronomers make an extraordinary discovery out in deep space. A cosmic megastructure, 1 billion light years long. The Great Wall.
You could put 10,000 of our galaxies end to end, and that's how big the Great Wall is.
Investigators are now racing to decode what shapes the most massive and mysterious structure in the universe.
Some force or process caused the Great Wall to be sculpted in this really particular way.
Can an alien-like creature reveal how the Great Wall fits into the cosmos?
This may be our best model of how the cosmic web was built.
And what strange force will define its future?
It too shall pass. It's not going to last forever.
To find out, we dive into the Great Wall's fiery birth and hunt for the weird cosmic glue that holds it together. To reveal how this megastructure rewrites our understanding of the universe on an epic scale. Our observable universe is vast. Astronomers estimate that it measures 93 billion light years across, and that it contains hundreds of billions of galaxies. From Earth, it looks like these galaxies are entirely separate from one another, solitary islands adrift in the expanse of space.
Almost all of the universe is empty. It's just cold and dark. We have telescopes that are looking farther and farther out, and there seems to be just more and more space between the galaxies, more darkness.
But astronomers today are finding patterns among the stars. This evidence shows that many galaxies share a mysterious connection. In January 2016, astronomers spot something huge. 830 visible galaxies, trillions of stars, woven into what appears to be a single flattened structure. 1 billion light years tall and almost as wide. This wall of galaxies is the most massive structure in the universe. Astronomers name it after the Baryon Oscillation spectroscopic survey that makes the discovery. The Boss Great Wall. What is this strange giant structure? The special telescope that finds the Great Wall has a unique way to hunt for clues. This is the Sloan Digital Sky Survey, or SDSS for short. SDSS works differently to a regular telescope.
Instead of astronomers saying, hey, I'm interested in that object right there in the sky, and pointing the telescope there and looking at it, the Sloan Digital Sky Survey tiles the sky. It's sort of squat and wide, and it has a wide field of view. So it sees a lot more of the sky in one image than a typical telescope. So you can create one big super image of the sky from it.
A quirk of physics allows this telescope to draw a special color-coded map that plots the positions of objects in the universe with pinpoint accuracy. This is how it works. As our universe expands, it stretches the fabric of space and forces objects further and further apart. This stretches the light that these objects emit and shifts its wavelength and color to the red end of the spectrum. The further away an object is from our telescopes, the stronger this red shift will be. SDSS can measure this red shift of distant galaxies to map the cosmos in 3 dimensions. The SDSS data reveals that the Great Wall is a clearly defined physical structure. It is deep as well as long. The body of the Great Wall consists of the densest concentration of galaxies ever recorded. And this makes it the most massive structure in the universe that astronomers have ever seen. Why is it here? How did it form? Astronomers believe the answer lies in the key building blocks of the Great Wall. Its trillions of stars. A star is a giant nuclear reactor that fuses atoms of hydrogen to produce light and heat.
From one end of the universe to the other, all the light we see out there is produced by the same simple thing, nuclear fusion. And that's true close by with our sun, and in the most distant reaches of the universe, it's our beacon in the darkness.
It takes a vast amount of collapsing gas to make the huge number of stars in the Great Wall. The Great Wall is not only the most massive structure ever seen, it is also the greatest concentration of hydrogen yet found in the universe.
The mass of the Great Wall is almost unbelievable. If our galaxy, our massive giant galaxy, were, say, the mass of a stick of butter, the Great Wall would be the mass of a car.
The Great Wall owes its genesis to a superhuge cloud made mostly of hydrogen that clumps together in one part of space. How does so much gas end up dumped in this region of the universe? A clue lies in the data that special satellites, like NASA's WMAP probe, beam back to Earth. The data draws this extraordinary image. It is a picture of the universe when it is just 380,000 years old. It shows the spread and concentration of ancient microwave energy. Astronomers call this the cosmic microwave background, or CMB.
The cosmic microwave background is literally what it says. It is a background glow of the universe in the wavelengths of microwaves. What it really is sort of the cooling off of the fireball of the Big Bang itself. It is a snapshot of the universe when it was only a few 100,000 years old.
The CMB captures the moment after the Big Bang, when the universe cools just enough for the first atoms of gas to form. The image shows that the concentrations of this matter in the early universe varies from place to place. Astronomers believe that the patches of the early universe with the highest concentrations of gas eventually evolve into structures like the Great Wall. But what triggers this unevenness in the first place? And what is the mysterious ingredient that glues the Great Wall together? The Boss Great Wall is the largest cosmic structure ever discovered. It owes its origin to a superhuge cloud of gas that collects in the early universe. But why does this material clump together here in the first place? Astronomers believe that the answer lies at the moment of the universe's creation. At a time when everything in existence fits into a space far smaller than an atom.
The tiniest sliver of a fraction of a second after the Big Bang, 1/10 trillionth of a second, the universe underwent an inflationary period where it went from about the size of a proton, a subatomic particle, to roughly the size of a grain of sand. Now, I know that doesn't sound like much, but you gotta realize this is a factor of 1,000,000,000,000 times. This is a huge expansion.
This moment of inflation sows the seed that grows into the Great Wall. Trillionths of a second after the Big Bang, the cosmos is a ball of energy where weirdness rules. Minute random fluctuations in this super hot soup create a pattern of hotspots on subatomic scales. As the universe expands, it stretches out the tiny hotspots over a cosmic scale. Energy condenses into matter, which provides the seeds for huge cosmic structures like the clouds of hydrogen that feed the galaxies in the Great Wall.
The inflation of the universe pulled parts of the universe that were close together wildly apart. If you had a region of the universe that had a little bit more stuff in it than average, next to a spot that had a little bit less stuff than average, given enough time, they would have smoothed each other out. But the inflation of the universe ripped them apart and they became frozen in place.
Tiny fluctuations at the moment of the universe's creation unlock the genesis of the largest structure in the cosmos. What is the invisible force that molds trillions of stars into the Great Wall's distinctive shape? The Great Wall is 6 billion light-years from Earth. This is too far away for telescopes to see in detail how it joins together. But clues exist closer to home that can help astronomers unlock the mystery.
Despite its ridiculous size and forbidding distance, the Great Wall is made of the same things we see around us. We can learn about that and then extrapolate that to understand how the Great Wall itself behaves.
Our Milky Way galaxy is just one of a cluster of over 30 closely spaced galaxies, known as the Local Group. And the Local Group is just a single fragment of an even greater collection of hundreds of galaxy clusters. Astronomers call this type of structure a supercluster. The Milky Way is part of a supercluster that is 100 million light-years wide. And superclusters pop up everywhere that astronomers look.
Almost every galaxy is part of a supercluster, and there are millions of these superclusters in the universe. Each one of them has tens to hundreds of thousands of galaxies in them, and each one of those galaxies has billions of stars.
The supercluster is the key that unlocks why the Great Wall has its distinctive shape. The Great Wall measures 1 billion light-years across. Breaking it apart reveals that it is a cluster of 4 superclusters. 2 of them are large, densely packed tubes, each more than 500 million light-years long. And 2 are smaller superclusters, each over 1,000 times the mass of the Milky Way. These superclusters join together to form a true heavyweight champion of the cosmos, the largest single object we have ever seen. Astronomers now know that 9 out of 10 galaxies sit inside a supercluster. What mysterious force brings galaxies together into these vast structures? A clue lies in the way that everything moves through the universe. Objects attract each other. The more massive the object, the greater the pull. Scientists call this force gravity.
If the universe is a symphony, then gravity is its great conductor. It choreographs the dance of everything in the cosmos. It brings clouds of gas together to form stars, stars together to form galaxies, and galaxies together to form clusters, including the Great Wall.
It sounds simple. Gravity pulls objects together into ever larger structures. But there's a big problem with this idea. From the Big Bang to the galaxies that we see today, computers can simulate how the cosmos evolved. When scientists simulate the formation of superclusters, these megastructures end up loose as gravity isn't strong enough. Only when they boost the gravity beyond the expected level does matter assemble fast enough to form the superclusters that we see today. So how can objects like the Great Wall form if gravity is too weak?
The only force in the universe that we know that brings things together is gravity. When it comes to structures as large as the Great Wall, there just isn't enough gravity in the galaxies together to form something that huge. Something else must be there underlying all of it, creating more gravity than we can account for.
Where is the missing gravity that the universe needs to make the Great Wall? And is the Great Wall unique? Or is it part of an even larger cosmic structure? The Boss Great Wall is a vast collection of galaxies that stretches over 1 billion light-years across. Scientists calculate that the gravity of its thousands of galaxies alone is too weak to build this immense megastructure. Where does the extra gravity that's needed to construct the Great Wall come from? Scientists believe that a clue lies in the space around galaxies. Gravity doesn't just pull on matter, it also bends light. When powerful telescopes photograph dense galaxy clusters, the objects around them look distorted.
This warping of space-time by a giant cluster of galaxies can act like an optical lens that magnifies the light of galaxies beyond it.
These strange smeared out images all over the sky. These are real. This is actually what you would see if your eyes were sensitive enough. You would see this in the night sky.
But sometimes, something weird happens. The light that comes from behind galaxies bends far more than astronomers expect. There must be an invisible material with huge mass and gravity around these galaxies. This material could unlock where the extra gravity comes from to build megastructures like the Great Wall. Scientists call it dark matter, and they estimate that it outweighs regular matter by a factor of 5 to 1.
Dark matter permeates the universe. We can't see it, but we know it's there through its effects. It has gravity. And if it has gravity, it must have mass. If it has mass, it must be made of matter that we can't see, hence the name. The question is, what is it?
The fact that dark matter appears to have weight is evidence that it is some kind of particle. If dark matter is made of particles, then physicists should be able to find it. Today, teams around the world hunt for this strange matter. This is the largest dark matter detector on Earth. It is called the LZ experiment. It sits in an abandoned gold mine 1 mile beneath South Dakota. The strange properties of dark matter mean that it is one of the few types of particle that can pass through solid rock to reach this tank. Inside the tank are 10 tons of liquid xenon.
This dark matter experiment uses xenon because it's really stable. It's not radioactive, it doesn't undergo chemical reactions. So if something happens in that xenon tank, it has to be external.
The theory is that certain types of dark matter will hit a xenon atom and create a characteristic flash of light. And if we see one of those, we have our dark matter smoking gun.
The discovery of dark matter will finally prove what creates the extra gravity that shapes the universe. It could also help explain the evolution of cosmic megastructures like superclusters and the Great Wall. In the early universe, it is possible that dark matter condenses and begins to flow to form a gigantic irregular matrix. Its massive gravity draws in the first atoms of newly forming matter in the cosmos. More and more matter condenses onto this scaffold, and its gravitational pull gets stronger. So this is where stars and galaxies form. They cling to their invisible frame of dark matter in huge structures, like the Great Wall's superclusters.
Dark matter is needed to give structure or scaffolding to something like the Great Wall. Dark matter is the critical missing ingredient for our understanding of how the universe actually works and how structure grows and evolves within it.
Dark matter solves the riddle of how the Great Wall gets its distinctive shape. But is the Great Wall unique? Astronomers scan the cosmos for clues. They discover that the Great Wall is not alone. They find similar cosmic megastructures lurking in the depths of space. Like this, the Sloan Great Wall. Its 5 stretched out superclusters contain an estimated 6,000 galaxies. This wall is huge, but it is only around half as massive as the Boss Great Wall.
We're calling this the Great Wall, but it's really the biggest Great Wall. We know of about a dozen others, and these are immense structures.
What is the link between these great walls? Astronomers race to find the connections between these megastructures. But seeing these links is a big challenge. Matter produces light in places where it is dense enough to form stars and galaxies. But precisely what lies in the dark spaces between these bright spots is a mystery.
So little of the universe is actually bright, glowing with starlight, and yet that's really the only thing we can see in the distant reaches of space. So we see these galaxies beginning to line up, but we don't really see the underlying structure. They're kind of like little fairy lights on a string, but we can't actually connect all the little bright dots yet.
In 2019, the Very Large Telescope in Chile makes a vital discovery. It captures an image of a cluster of young galaxies, 12 billion light years from Earth. The young galaxy's newborn stars burn super bright. Their intense light illuminates areas of space that are normally too dark to see. This cosmic flashlight shows that immense clouds of hydrogen fill the space between galaxies.
Discovering this material was an absolute game changer because it allows us to see structure in the universe on galactic and intergalactic scales for the very first time.
Astronomers think that vast invisible clouds of hydrogen like these run between all galaxies. But how do gas and dark matter weave together megastructures like great walls that are separated by billions of light years? And what shape is this giant cosmic network? In 2016, astronomers discover the Boss Great Wall. They suspect that it links to similar structures spotted throughout the cosmos. But how do these megastructures join together? A clue lies in the way that the gravity of dark and regular matter shapes the superclusters that make up these great walls.
When you think about things pulling together under the force of gravity, you would assume the universe is very good at making big blobs, everything just orbiting around everything else. But at the scale of superclusters, the galaxies form very interesting, very well-defined shapes.
The observable universe contains an estimated 10 million superclusters. The galaxies in 70% of these structures appear to line up in long shapes called filaments. Astronomers believe that a quirk of gravity unlocks why so many are this shape. The Big Bang scatters energy across the universe, where it condenses into huge elongated clouds of matter. Gravity squashes an elongated cloud to a point where dense areas collapse to form stars and galaxies. Next, gravity attracts the densest parts of the cloud to each other. The gas and galaxies flatten into a sheet. Gravity then draws together the densest parts of this sheet to eventually form long filaments. Astronomers think that the way gravity molds gas and dark matter on a huge scale provides a clue about how the Great Wall joins to the wider universe. Starting soon after the Big Bang, gravity sculpts the gas and galaxies of the early universe into sparkling tube-like superclusters. The bright galaxies inside 4 superclusters form the distinctive shape of the Great Wall. But the Great Wall may not float alone through space. Its superclusters could stretch for many more millions of light years and intersect with similar tubes of gas to make a cosmic web, of which the Great Wall is merely a part.
Galaxies are not randomly strewn throughout the universe. They form into superclusters. Superclusters aren't randomly strewn throughout the universe either. They form a pattern, a web of filaments. This pattern is telling us about how the universe is built on an immense scale.
The superclusters in the Great Wall could be just the bright visible sections of super long invisible threads of gas and dark matter that crisscross the universe. What is the shape of this cosmic web? Researchers at the University of California, Santa Cruz, believe that one of Earth's strangest creatures might unlock the mystery. This is a slime mold. The entire organism consists of a single giant cell. Slime molds thrive on bacteria and rotting matter. But this food is spread out. So this strange organism has a cunning strategy to scavenge the greatest area using the least amount of energy. It grows a feeding network.
A slime mold is a very simple organism. It lives in decaying vegetation. They actually send out little tendrils. The tendrils connect, and the slime mold grows over time. So you have this larger web-like structure evolve.
The researchers believe that the algorithm the slime mold uses to search for food could predict how the universe weaves great walls into a cosmic web. The researchers decode the algorithm that the slime mold uses to build its network. And inject it into a 3D model of 37,000 nearby galaxies. This is the result. The virtual slime mold sees the galaxies as food and builds a network between them. This network predicts the exact paths of the invisible filaments of gas and dark matter that link the universe together. But does the slime mold match the pattern of the real cosmos? And how big can the great walls in this giant web get? The Boss Great Wall is the largest structure ever seen in the universe. Many astronomers believe that it is part of a larger network of gas filaments that weave superclusters into a vast cosmic web. One theory is that the way a simple slime mold grows its feeding network can predict the actual layout of these filaments. But can a single-celled organism on Earth really reveal the shape of the cosmos? There is a way to find out. The Hubble Space Telescope photographs nearly 1,000 quasars between 1990 and 2020. Astronomers think that quasars are supermassive black holes at the hearts of distant galaxies. The massive gravity of quasars superheats the matter that gets close to them. This energy produces an intensely powerful light. Some of the predicted gas filaments sit directly in front of a quasar. The pictures from Hubble show that the light it sees coming from these quasars is dimmer than expected. This is strong evidence that invisible gas filaments block some of the light. The cosmic web that links superclusters and great walls across the universe really could be the shape of a slime mold.
The universe really produces some weird connections, and one of the weirdest is the fact that the networks and connections that the slime molds make with each other looks a lot like what we see in a large-scale structure.
Scientists do not know for sure why the slime mold and the universe grow into similar shapes. Both networks appear to follow a hidden mathematical rule that allows them to fill the maximum volume of space with a limited amount of matter. Astronomers believe that great walls are the largest, densest patches of galaxies and gas in a vast cosmic web. And thanks to the tiny slime mold, we can now see how these vast megastructures connect across the universe. The Boss Great Wall is huge. But is there something even bigger out there waiting to be discovered? Astronomers think that the answer hinges on the outcome of a battle between two forces that shape our universe. The first force is the pull of gravity.
Gravity attracts things together. And not just that, the closer you are to something, the stronger the gravitational force. So all across space, you're attracted to your nearest neighbor. That builds up structure from galaxies to clusters to superclusters and larger.
The second force is the push of the Big Bang.
On the very largest scales, we have the force of expansion left over from the Big Bang itself that has caused the universe to grow 93 billion light years across over the last 14 billion years.
The universe will build ever more massive structures if gravity beats the force of expansion. But structures can't grow bigger if expansion pushes matter out of reach, faster than gravity can gather it together. Finding a structure greater than the Great Wall rests on unlocking which of these two factors is the more powerful.
And so, to figure out how much pulling together and pushing apart there are, we need to make a very precise measurement of the expansion rate of the universe.
Astronomers at Arizona's Kitt Peak Observatory get a front row seat at this cosmic contest. This is the Mayall Telescope. It measures the distances between thousands of galaxies. Astronomers compare the average distance between galaxies today with the distance between galaxies in the younger parts of the universe. This comparison charts the speed of the expansion. The data from the Mayall telescope reveals something extraordinary. The expansion is getting faster and faster over time. This acceleration puts ever greater distances between the matter the universe needs to build superclusters of galaxies. This means that there is a limit to how big great walls can get. It is possible that the Boss Great Wall is the largest structure in the universe. Why is the expansion of the universe accelerating? And what does it mean for the future of the Boss Great Wall? The Boss Great Wall is the largest collection of galaxies ever discovered. And many astronomers think that its size is the largest that any structure will ever grow to. The reason is the discovery that the expansion of the universe is getting faster and faster and driving galaxies further apart. Why is this expansion accelerating? A clue lies in what happens in the coldest, darkest, and emptiest parts of space. In 2019, scientists in Zurich, Switzerland, detect tiny energy fluctuations in a vacuum chamber, chilled to just above absolute zero. These bursts could come from strange exotic particles that pop in and out of existence. Their energy produces a tiny outward force, like a small push on the fabric of space itself. In places where there is lots of matter, like around planets, stars, and galaxies, these minute effects go unnoticed. But in empty regions of space, like the voids between the threads of the cosmic web, it could be a different story.
This whole time, we've been letting our eyes be drawn to the bright parts of the universe, this beautiful cosmic web that stretches across space. But if you look in between the filaments, there are these vast voids where there is almost nothing. And could it be that very empty regions of space behave in some fundamentally different way?
Scientists pin this different behavior onto a weird, hidden force called dark energy. The way dark energy works could explain why the expansion of the universe is accelerating. The tiny push from dark energy expands the space around it, like an oil bubble growing in clear water. This new space contains dark energy, and the push from this new dark energy creates even more new space. This never-ending cycle continuously increases the amount of dark energy. The expansion of the universe accelerates. And this could signal the end for structures like the Great Wall. As the megavoids grow, they flood the space around them with dark energy. And the Great Wall is right in the firing line. The dark energy rips the superclusters from the Great Wall and tears them apart. The dark force is so strong that it shreds superclusters into their building blocks. Eventually, the galaxies themselves disintegrate. They leave stars and planets drifting alone through space. with skies devoid of starlight.
We live in a special time in the universe, the era of superclusters. The universe is expanding. Moreover, we think that expansion is accelerating. It's expanding faster and faster every day. This spells doom for the Great Wall, because eventually dark energy will tear clusters apart.
The Great Wall is a wonder of the cosmos. It is a vast assembly of gas and galaxies that stretches over 1 billion light-years of space.
Even though the Great Wall is one of the largest known structures in the universe, it's so ephemeral and so easy to miss. And so its actual discovery has been one of the great achievements of observational astronomy.
Astronomers now know that the Great Wall is just one small part of a network that holds everything in the universe together.
A giant cosmic web of trillions of galaxies stretching billions of light years across the universe, filling the entire space. It's just mind-blowing.
Quantum fluctuations, frozen in time trillions of a second after the Big Bang, lay the foundations of the Great Wall. Dark matter then chisels out the megastructure when the universe is young. Dark energy threatens to tear it down billions of years from now.
The universe appears to be almost ripping itself apart. Even superclusters, even clusters of galaxies may not survive dark energy.
We have never seen anything quite like the Great Wall. And we may never see anything quite like it in the future. But while it lasts, it is one of the biggest highlights of the cosmos.